Hello everyone and welcome to a new set of notes here. You may notice that this set of notes will be about piecewise functions. And in this intro, whenever the time hits a certain marker, you might notice... let's get started before the next... Alright, as I mentioned, our notes today are about piecewise functions. What are they? How do they work? That's it, let's get started. First off, in piecewise functions, you should know that they're composed of multiple pieces of functions sort of stitched together to make one whole function. So they may look like multiple functions separated out, but together they make one function. Now, they don't always have to be connected. Sometimes a function is discontinuous. So a discontinuous function here, where it jumps, right? Or a continuous function where it connects the entire distance. You should know that a continuous function will be continuous across the entire domain and range. Otherwise, it doesn't count as continuous. So, for the first of our 3 examples today, we're going to look here at solving for each input and then sketching the graph of the function. Now, you'll notice that I don't have a grid set up on this. In fact, I'll set up the grid for the next part. I'm going to start with the inputs, then we'll do the graphing after. So, for starters, how would I go about solving for the inputs 4 or 12? Well, as you might predict, I'm going to put 4 in for x. And once I do that, I have to identify which of these pieces of the piecewise function that will go into. So where does 4 fit? Less than 3, between 3 and 7, or more than 7? Well, I'm going to put it here. And that means that when I plug in 4, I'll have 4 minus 5 squared. And negative 1 squared will be positive 1. When I go to plug in the 12 afterwards, I have to go back. I have to go back and reset the rest of the information from when I had the 4 before. And I'm only going to consider what happens when I plug in 12. Well, when I plug in 12, I need to go down here since it's more than 7. So I'll have 24 minus 10, so a result of 14. That's it. Whenever you deal with an input, do one input at a time, and make sure you're redirecting each input to the correct piece of a piecewise function. So when it comes to taking all of those inputs and outputs from the piecewise function, what's it look like to graph it? Well, you have to try out a lot of different inputs to get a piecewise function put together, because here we have 3 different portions of a single graph. So if I start with numbers below 3, like 0, 1, and 2, I'm going to notice that 0 plus 5 is 5, so 0 and 5 will be my first coordinate that I graph here. If I do 1 and 2, I'll have 1, so negative 1 plus 5 is 4, and 2, so negative 2 plus 5 is 3. My linear function here should fit as per mx plus b, where the slope is a negative 1, and it starts at plus 5. But I cannot put 3 into this function. I can get close to 3, but I'm going to have to stop. I know what happens on the backside of this. It continues going, and I can even put an arrow on it. That part of the graph is done over here. However, if I get to 3, I don't know if this is going to, say, have a jump and be discontinuous, or maybe even be connected to the next portion. I don't know. I have to put in 3 for the next section, since it has the or equals to on it, and see what happens there. Well, as it so happens, if I put 3 in for this function, I get 3 minus 5, so negative 2, squared is 4. So if I put that point here, and it does need to be a solid point because it's included, that's a jump. It's not going to go from 2 to 4 without having to leap. So this will be an empty circle here. This graph, the first one, is done now that I've placed that empty circle at 3. Next, for my quadratic, I see here that it's translated to the right 5. So 1, 2, 3, 4, 5. And from here, it will be a standard quadratic.
2 hours later.
Finally, what happens when we plug in anything more than 7? Well, let's try it. Say I just put in 8. It's a pretty safe choice. I'll be able to see what happens when I plug in 8 here. So 16 minus 10 is 6. So I can place a point at 8, 6. And I'll graph that line this way. But you might notice that if I were to graph the other direction, this part of the graph is continuous, since it does match up at that coordinate there of 7, 4. At this point, we're done graphing. We've graphed all 3 parts of the piecewise function, and that's what they're looking for on this problem. All right, so that first example is the longest by far of this set of notes, because all we need to do now on the next example or 2 is modify or recreate an equation of a piecewise function. So we need to write the piecewise function for the graph. And you'll see here there are 2 parts of this graph. So when we go to make our piecewise function for f of x, it needs to have enough space for 2 different functions. And I'm going to start with the domain of each. So on our first function here, which seems to be linear, domain will be all numbers below 0. So all numbers below 0, but not including 0, because at or above 0, we will have the other function. Now for the first function here, I can see that it's going to go through this point here, and it would go through this point if it kept going. So what is that? It's linear. It's going to go down 3 over 2. So that tells me that if I'm going to write an mx plus b here, I need down 3 over 2x. And my intercept, where that hole is negative 4. So my function, negative 3x minus 4, represents the left side of the piecewise function. And on the right side of the piecewise function, I'm going to list the square root of x. But in this case, it's translated down by 1. So as long as you write each part of the function for the domain that it's in, you're done. Finally, what happens when we try to transform piecewise functions? Well, there are 2 main characteristics here, and you will need me to move my face so you can see them. First off, when we do something like a vertical compression, here, it will only affect the function and not the domain values. Well, what's that mean? Well, it means that each of these, see, what I do to the function, I have to do to each piece of the function. So what would have been a regular function now has 0.5 in front of each value. Something like that. So the only change here is the 0.5 in front of each of the functions, because the function itself overall has been halved. For part B here, we're going to be translating the function to the right by 2. And that's different. In that case, we actually have to consider what happens to the domain. See, replacing x in the function with x minus 2 is going to affect nearly every portion of the piecewise function, since I have to replace x with x minus 2 in each of these places. Now see, plugging those in is great and all, but now I have to simplify each part of this.
2 hours later.
Now, in some places, this has had a somewhat predictable effect. For example, in here, with my x domain values, everything has just shifted to the right 2, which is what an x minus 2 would do. This is a shift to the right of 2. However, it's also changed the functions, most surprisingly in the top row. And this not only changed it by moving it to the right 2 here, it also completely changed the top row, since we had to distribute x minus 2 through a square and then add 1 at the end. So this represents our answer for letter B, h of x, because every value has been replaced with x minus 2 on the input of the problem. And that brings us to wrapping up this set of notes. Oh, let's move me back. But please notice here that there are a few different things we've gone over today. For starters, we've taken a look at whether or not you're graphing it, you're writing it, or transforming it when it comes to piecewise functions. If you're graphing a piecewise function, make sure you test inputs for each part of the piecewise function, and then graph each piece to get a complete picture. If you're writing a piecewise function, be sure to start by identifying your domains, and then identify the functions from each portion of those domains. If you're transforming a function, that transformation affects each piece of the function. And if you're dealing with effects that change x, be sure to replace x everywhere in the function. Not just the pieces of the functions, but also the domains in between. I hope that you find this video helpful, and I'll see you in the next one. All right, bye!